graduate students worth at least $1 million. And that was a few years ago, so it must be 10 million now. And I'm sure it's held out. So anyway, let me introduce Steve, and we'll get going with the program.
Let's see what we're going to do here. Let's see if we can pull this out of here.
You probably know how to use one of those.
Well, let's see. No, we got. Yeah. Here. It should be already there. Let me get this.
It's not.
And then this. And we got it. Good. Good. Donna, you have the pointer? Chance. Here we go. It was 2 years for electron diffraction. 2 years! Which is about as much French as I've ever learned. There we go. Yeah, I was given a challenge here to give the transition talk between the Rochester days and what we're doing in Michigan, and then beyond that to Picometrix. Let me get this tied on here. Is that good? And this was a challenge for me because it's the terahertz thread that runs through those three groups. And the first part in Rochester, I had actually nothing to do with terahertz. In fact, what we did in terahertz in Rochester is quite different than the projects you've been hearing about. The projects you've been hearing about had big bangs. They were spectacular. There was a lot going on almost at the moment you heard about it. But with terahertz, we were planting seeds. And this was a formidable seed that we were laying down that would take root. But Rochester really didn't get into terahertz until actually we left in '88. So I want to talk a little bit about that. Not going to get deep into this. But for those who don't understand the terahertz regime, that radiation band is a very difficult one to adhere to tap. We call it the terahertz gap because it's difficult to access from the optic side as well as from the electronic side. And so it's always been very, very difficult for us to access that. And up until now, there was some work done by Button and Afsar years earlier for spectroscopy purposes, systems a fraction of the size of this room where they were using thermionic emitters and whatnot, and all they were really looking at was spectroscopy for different kinds of materials. And everyone that understood and spoke about terahertz, and in that case we referred to it as millimeter, submillimeter wave, they would talk about that as a virtually useless part of the spectrum. And the large part of that was because no one knew how to access it. And what was shown in Rochester was the first application of photoconductive switching with a microwave radiation waveguide. And this was done by Gèrard, as well as Charlie Stancampiano and Dan Blumenthal, who's in the audience with us today. And Dan, Steve, to your point, was also an undergrad. And at this point, what was going on in the laser lab is Wayne was working on chrome-doped gallium arsenide on the street camera. I was doing chrome-doped gallium arsenide on impact ionization and switching 5 kilovolt pulses, which later, Gèrard, we found Boeing was using on a secret mission for stuff related to radar of their own. And so Gèrard had this idea of inserting that into a waveguide and using it for radiating an impulse into free space. And he got in touch with the electrical engineering department, and this is quintessential Gèrard. He is the guy that is going to network par excellence on all of these different topics. He knows how to surf that crease between different disciplines, in this case, the lasers, the semiconductors, and now getting into the microwaves. He finds the right people to work with, and we capitalize on it. And that's an absolutely beautiful talent. That is something that we can all learn from. And they teach that. They try to teach that more. We were learning this back when we were undergrads, and it was a great time. So I just want to just walk through this here. He had his little photoconductive switch. It was in here. It was going to generate your signal, and it was going to propagate through. It was going to hit this semiconductor here, which was germanium. And with part of the original optical pulse that was creating the switch in the first place, he was coming over here, and he was going to create a plasma in that semiconductor, render that a mirror, and reflect a portion of that signal back through onto the oscilloscope. And this is one of those waveforms. And by simply moving the prism, of course, you can walk this through, and you can trace out your signal here. Looks like, are we still focused on this? It looks like it's getting fuzzy, or is it my glasses here? Nevertheless, what ended up happening then, and of course, we could map this out with great precision, and so we found that the waveform was exactly the optical waveform of the order of 50 picosecond, despite the fact that the germanium here was itself turning off in a microsecond or even a millisecond. So this was the first use of a photoconductive material for optically generating and radiating a signal. And even though it wasn't terahertz, it laid the groundwork for that. It was that planting of the seed. And it provided not only the photoconductive switch, which was very high in its sensitivity relative to other techniques, but also this means for synchronous pump probe. And we would have to wait for Dave Austin, years later, to come up with the symmetric system of having antennas for both the transmission as well as the receiving, and to make beautiful oscillations so we can get to amplitudes, so that we could get into the terahertz regime. We had to wait for the hyperhemispherical lenses. We had to wait for a number of these things. The integration of the switch with the antenna. These were all key things that were not coming about in this experiment. But just the same, I want to point out here, for those that didn't, Dan's in the audience here. This is Dan, our trailblazer. Ted Norris, who you'll hear from next. Mo Pessa, who did the rubber band laser, which was one of the components to this. And he's, by the way, just making sure our tour guide here doesn't lose anybody else. Warren S. Warren lost about a mile up the river. I also fell off in that same incident. And I swam back to the boat. My teeth are chattering the whole trip. I think it's the beginning of hypothermia, actually. This is the Roaring Fork. It was an incredibly cold river. But back to my point here. We find that if you look at this and you start to plot and you look at what terahertz papers were being published, this is not a big bang. It is a seed that was planted. And it takes time, but it's nevertheless growing, and it's growing at a pretty good clip. But we've had for at least through the 80s and 90s, it was an elitist club that was involved in terahertz. And this shows in the 90s Martin Nuss's terahertz lab at Lucent Bell Labs. And this is Stefan Hunch. And this looks like, New York City at nighttime. There's $1 million worth of equipment here on this table, and a number of years to develop this technology. But it was nevertheless exciting to see that it was taking root at Bell Labs, and Giannis joined Bell Labs, as well as Doug Dykar and Earl Dooling, then went off to Dan Gruszkowski's group at IBM. And so there were these other places that this pollination was taking place. All the while, nothing was going on in Rochester in free space terahertz. But what we were doing is still working on those ingredients. And one of the papers that we worked on, again, not me, but the team here, is done by Doug Dykar and Shantanu Gupta, Mike Frankel, and Gèrard, as well as Tom Zhang. This work is the showing of the first LT gallium arsenide. LT gallium arsenide is the semiconductor that was discovered more accidentally than anything else by Bob Kalawa came back from lunch, realized his MBE reactor, the heater had broken, cooled down, post-annealed it, found it was a fantastic material for stopping the gating, backgating of charge in transistors. But a year or two later, with Gèrard again involved in a contract with Jerry Witt, knowing Bob Kalawa, they got together. Frank Smith was a new student there, and we did the very first work, and we showed that this stuff is incredibly fast. This really had some great legs. So, this is about where we went. I want to back up one thing here and just say at this location that I wouldn't be truthful if I said I had no contribution to this first work. It happened in a lab that I was working on where I was doing my impact ionization work for this avalanche switching of chrome-doped gallium arsenide. And we realized that we needed to drill that hole in that waveguide. And it's nothing for me to get in the machine shop, drill a hole. I wouldn't know if Gèrard would go in there and harm himself, and certainly the rest of these guys wouldn't be involved. So I take the waveguide and I walk back to the machine shop, and as I'm walking past the stairs, there's Moshe Lubin and Len Goldman, the director, the deputy director. And they see me walking what looks to be with a piece of plumbing. And Moshe Lubin asks, what is that? Now, I've never at this point spoken with him. I've been there maybe a year and a half. And I know him to be the founder of the laser lab. And I explained to him, just as I've just explained to you, what's going on here. And he's intrigued. He doesn't touch it. He looks at it, and he says, I want you to take that waveguide up the stairs to Gèrard, and you put it on his desk, and you tell him you're wasting your time. And I would have said nothing in that moment. I dutifully went up those stairs, and I went to Gérard's office, and I put it on his desk, and I said, we have a problem. We have a problem here. Gèrard, though, he has this ability to see through this crystal ball, which is polished better for him than for others like Moshe at this point. And he knew that deep down inside, these lasers were progressing to the point where they were getting faster and smaller and more high power and everything that we needed in order to bring to fruition and possibly even commercialize this terahertz work. And so you, Gèrard, and Moshe must have had a talk about this. Within hours, we were busy working on this, and we got those measurements. And that was, to me, it was a learning point to hear that. Anyway, I want to jump back here, and this is where we jump off in Rochester. We've done a lot of work in Rochester at this point. I've been chartered to talk about terahertz. So I could have easily have talked for an hour on picosecond electron diffraction and all that went on there. But the reason that they wanted me to talk about terahertz will follow as we now move into Michigan. This is the Rochester to Ann Arbor transition team, as I'd like to refer to it. And what we have here is everybody that was involved initially. There were a couple that came in later, Don Umstutter and a couple others, but you have John Neese and his wife, Philippe and Sue, my wife, Elba, of course, our fearless leader and his wife, Penny, Ted, myself, Sue and John, and Giannis and Mara. So this was the team. Giannis at this point was deputy director of the center. This was the group that was going to be the framers for the CUOS Center that came from Rochester. A lot of other people were involved. Giannis had just come back to our group from his days at AT&T, Bell Labs, where he was working with Dave Austin. And so he was, of course, the expert in electro-optic sampling. And this whole team brought with them, there was a lot of equipment, but more importantly, a lot of energy. We had a lot of opportunities. We could have gone to University of Florida, Gainesville, could have gone to Berkeley with Livermore, Urbana, or Ann Arbor. And we chose Ann Arbor for a few reasons. One of those reasons was it was close to Rochester. We could all come back to family and homes and whatever we had here or in Rochester. But also, they had a fantastic microfabrication facility, which we knew we would need for these kinds of projects like the work with terahertz. But we allowed the students to weigh in, and they were unanimous. We want to be part of a big football team. And so off we went. And one of the first things we did was we went back and we looked again at the LT gallium arsenide. And this material, it just had legs. It just was unbelievable how fast. And once you started to make this with very fine finger spacings, you realize you could hold to the sub-picosecond response, but with its high mobility, you could have high responsivity and at the same time maintain the high breakdown voltage. This is the trifecta in these semiconductors. Microfabrication allowed us then to get into a number of new avenues. And it was new for us. Lasers were continuing, but now we can marry it to new devices. And so we built a lot of new devices. We got into waveguides. We got into new photoconductors. I was working on transducers at that time. And one of the papers that we wrote with Shantanu John Whitaker and the group out of General Electric did the very first work in LT indium gallium arsenide. And this was going to be the basis for liberating us from Ti-sapphire lasers and to move into fiber lasers that would then further reduce the cost and make the systems more compact. I put this also was in the paper. It wasn't about the InGas, but it's important because this is going to be my jump-off point. I was with the university for 4 years, and at this point I realized this was a great opportunity. There were new devices. I was able to write my own proposals, and I was going to start a company based on very high-speed detectors for telecommunications applications, or at least test and measurement. Work continued, nevertheless, and this is a group out of CUOS. Thierry Motte was continuing with high-power switching with LT gallium arsenide. Jim Huang was actually helping us on some of our early amplifiers on our systems for terahertz. Jim Schwalik was the guy who was really driving further work with terahertz at CUOS. He was doing all the spectroscopy. He was doing the cryogenic work. And with John and Ted's leadership, he was even taking the first of these antennas that were LT gallium arsenide and making transmitters and receivers. So there was a lot that he was contributing to the future of the terahertz work. The guy here on the left, on the right of Jim, is Van Rudd. Van later joined us, and he made a critical contribution to the terahertz work when we started Picometrix, in that he used his PhD work in fiber in compression and dispersion compensation to develop new techniques for us to make fiber pigtail terahertz heads. So we'll get into that also in a moment. And of course, John Whitaker to this day continues in terahertz, but his work is more now into applications. For over these years, the cool thing that has occurred is that we don't all have to be experts in making terahertz. Now we can actually get on with doing things with terahertz. And so I start Picometrix in 92, was ionized in 91 to do this through a meeting that I had gone to in Boston. A lot of long stares at the ceiling late at night, asking myself, well, why am I going to do this? We had just raised umpteen $1 million with the center. I was the de facto industry liaison for the center. I could have stayed there and done that work. And Gèrard said, you can always come back. You can always come back and get that job. And at some level, I did not want that safety net. That was, to me, I was very appreciative of it, and it was great that he offered it, but you have to know there isn't that safety net if you're going to walk that wire all the way across and not fail. But what he did do for us was he said, why don't you guys just sit tight here in the labs? And he provided me with a square foot of laser lab table. And I had that for maybe 6 months. And it was great. And we laugh, and it's funny, it is. But the fact is, there's a lot of insecurity in wanting to start your own company. There's so many things you got to know, and so much you're learning along the way that you just don't know. So it was nice to be still within the community of people that I had known. And we then progressed past that. In the second year, Giannis joined us and Jung Ho Kim. And here we are with a sizable part of a lab's room. And we are developing our first products that would later go into the Newport catalog. And all this is based on the MSM photodetectors that we had published at the University of Michigan. Was LT gallium arsenide. It's the first product with LT gallium arsenide. And it's still to this day, I believe, the fastest photodetector that's out there. So we've pushed on that. Today, just jumping ahead on this, the contest was in this area. We were building this out, and we were doing some work, even with Mike Frankel, on some military applications or defense applications. But today, we have all sorts of different photoreceivers and photodetectors, from 100G photoreceivers up to new APDs that we're developing, which are holding great promise. So there's a lot going on today, but for the first 5 years, what we were working on was predominantly test and measurement for Tektronix, Newport, companies like this. And then, and I should mention that we had a roadmap. We had ideas of what we were going to get into, but we were consumed in doing this. And then I got a call from Martin Nuss. And Martin says, Steve, I have to talk to you. We have an application that we can't touch. And I said, well, what is it? He goes, it's all terahertz, and I have a proposal for you. I can't tell you who this company is. I said, I can't get near that right now because we're so busy. It would have to be something they would fund it, and, oh, they'll fund it. I said, it's not enough even that they fund it because there's a potential for missed opportunities doing this. I mean, Martin, it has to be a killer app for me to do. Oh, it's a killer app. So after we sign the documents, we find that it's with Philip Morris. And Philip Morris is under pressure to eliminate all of their beta gauge sensors in their tobacco lines in Europe, because we all know we don't want to die because of beta gauge radiation being probing of your cigarettes. So we were tasked for a number of years to understand weight and water in tobacco products. And we learned an immense amount about terahertz. We were fast-tracked because you won't find an industry that makes more product than this one. Whether you like Philip Morris or not, they make 1 trillion of these products, and it's amazing the science that goes into this. Yeah, right. It was a big deal. Apparently, they even helicoptered into Humdale and talked with these guys. And okay, but there was another thing going on. Not only were there the lawsuits against all of Philip Morris and big tobacco in general, but let's face it, Lucent just got started. You know, the last thing they want to do is, have any image issues beyond, trying to make a go of it as they were. So, long story short, we're no longer working with Philip Morris. We actually worked with them to the point where they were able to transition this to a microwave application. But what they did for us is they accelerated the development of our system to the point where 20 years after Blumenthal's paper, we now had the first terahertz system commercially available. And with it, it came with fiber pigtailed modules. This was a very powerful tool for us. This is what Van was working on. And now we progressed to 2003, where when the Space Shuttle Challenger had its accident, we were able to step in 50 meters worth of cabling. We can still hold 100 femtoseconds on our antennas. We scan the entire tank, and we give them this perfect photographic quality imagery through the SOFI, the foam that's on there. And today, we now have our 5th generation system, which takes now not only the submicron microfabrication, but also the LT indium gallium arsenide that we had developed when we were in Michigan. We've added a few other things with it. This is a near all fiber-based system, a UL qualified, 0 to 50 degrees operation. You can actually get a system like this that is cost competitive now to ultrasonic applications. And from this one unit, we can split off and we can have any number of heads. So in these factories where there are lots of lines running, one can imagine having a singular box and many terahertz heads running. We can do spectroscopy with it, but we can do gauging. We can measure down into the microns if we want to. This is Earl, our director of business director, and Greg Suha is also in the audience here, who is our senior scientist in all things optics. And this is our new probe that is being used right here on a tank. And you can't get in this tank and make these measurements, but this can make those measurements very fast. And you can put that on a robotic end effector arm, and you can make these measurements quite rapidly. Defect identification, process control. This environment here is where it's 100, 120 degrees C, and the terahertz runs beautifully in that application. And it's dropping new kinds of materials on there with a precision that allows them to get high quality coming out. Medical applications, material properties, we can look at DLAMs, we can see embedded layers to see the quality of those layers or what they're made of. And further to that, you can do imaging with rapid imaging systems as well as their XYZ, and art conservation. And John Whitaker's doing work in this, and of course we're doing work with Gèrard, and here we are again, we follow through because Gèrard once again is in the thick of this. He is now interested in art conservation, and he has worked with us, and now it's more of a family affair. For we have Gèrard, we have Marie, and Marcel in the background, and it's only a question of time before we get Julian involved with automobile parts. He's been in our lab, so Gèrard is forever pushing this new technology, and down the road we'll even have Vincent involved when it comes to chocolate. Yeah, to do inspection of, yeah. So I didn't want to leave it right like that. I did want to leave it with, as Wayne had said, it's not Gèrard alone, it's Gèrard and Marcel who have made all this possible and actually bring us all together. And for the two of them, this is a wonderful family affair that we have here, and congratulations to both of you, and happy birthday, Gèrard. It's wonderful. Let me give you that part.
And so since we're so on time here, I won't say much, but just introduce my friend Ted Norris, who took over as the director of CUOS when Gèrard scurried back to France. And here you go, Ted.
Okay, thank you very much, Steve. It's a great honor indeed to be here and get a chance to talk. And I was tasked by Herb to give a history of CUOS. I entitled it A Personal View because, of course, I'm completely biased here. This is going to be my own journey a little bit through this. I make no claims to historical completeness or objectivity or anything like that, but I'll really try to give, hit the highlights for what CUOS has been all about, particularly through the 1990s when it was an NSF Science and Technology Center, and of course as an excuse to show pictures of us when we were a lot younger then. We all have our own stories about how we ended up in optics and lasers, and of course there are many accidents in history that get us where we are. I first got interested in lasers as a junior in college, working with Bob Hilborn, who is a very well-known physics educator. And it was he who suggested that that maybe Rochester would be a good fit for me in graduate school. So, I went to Rochester intending to do quantum optics, and there are lots of famous, very senior people there in quantum optics, and I very thoroughly, went around and talked to all of them and they'd lost their money. You know, their funding had dropped, and it was just really bad timing. But Professor Mandel said, well, I hear there's this guy over in LLE who maybe has something. So I went over, and Gèrard took me on and put me in the famous room 116, and where we were building lasers. I learned everything I know about lasers from Jim Kafka and Earl Dooling and Todd Sizer in there. And my first year, I was a first-year graduate student. I didn't get much done, and sort of learning from the senior guys, and I'd had a little accident. I lost some of my teeth, and I was kind of coasting for a while, and Gèrard sat me down and said, okay, you've been here long enough. It's time to contribute. It's time to do something. Yes, I agree. What? He didn't give me a project. He didn't say. So that's visionary leadership right there. I knew I had to do something. That's a lesson I learned, from my students when I tell you it's time to do something, and I don't tell you what. Well, of course, the secret is you give a student half a problem. You only partly define what it is that you're going to do. And he said, well, maybe we should work on the dye laser. And I've heard of this anti-resonant ring concept here. So the idea was to go in and let me pull this back up, and build basically a synchronously pumped dye laser that you could also colliding. I'm pushing the wrong buttons here. Yeah, there we go. So it's a synchronously pumped dye laser, and it's got a jet in here in the anti-resonant ring, so we can do colliding pulse mode locking at the same time, and then synchronize it with the kilohertz region up here and make white light. And as Wayne has told you the whole story, of course, we were a few months late to the table, but it worked beautifully, but we learned a tremendous amount from this thing. Of course, we just got my first patent out of this. Little were we to know, of course, that Ti-Sapphire was only really a few years down the horizon. So, of course, all these dye laser things, nothing happened with. Of course, you have the obligatory public relations photo with Gèrard, wearing the tie, which looks like it's just about to hit the watt of green. You can't see behind, but this curtain is full of holes, as we occasionally misalign the laser into it. And of course, as the graduate student who just spent hours getting this thing going for the photographer, and of course, we're all standing there with our dust-off cans upside down, blowing onto the table so that the photographer could get all the beams. So that then the cost of this was that after this photograph was taken, we spend the next 5 hours cleaning the optics so that the lasers would still work again. But of course, now I'm in those shoes, and with the PR photos, and my students are hoping that I won't actually touch the knobs. Okay, so then 1988 was the move from Rochester to Michigan. This is Gèrard in the I keep pushing the wrong button, in the office working on his lasers class, getting ready for class. Of course, Autumn Kraft. I don't think it's been mentioned yet. She played an absolutely central role in moving the group to Rochester and getting everything set up, and I think keeping Gèrard on the rails during the whole process, if I fairly describe that. And of course, Giannis, I don't know where I got that picture, came up from Bell Labs, and we started out in the EECS building and then moved over to the IST building. And of course, John Neese came along. You see John Whitaker, very well dressed, not his typical laboratory clothes. Steve looking like something out of Mad Men, I think in the 60s, wearing the white shirt and tie here. Don Umstatter came up from Bell Labs. I came in the winter of '89 before I went on my postdoc to France, to get the dye laser system up and going there. And of course, Don Umstatter came, and of course, one of the highlights of this was, of course, getting Emmett Leith involved in the whole thing, and teaching him about femtoseconds, which of course he then went on to do fantastic things with. And by this time, of course, there have been quite a few graduates from the group, and CLEO was always the place to get together. I don't know the exact year of this picture. Maybe I'm guessing 90, or perhaps 89. I don't know what you guys are excited about there, but there's something going on. So this was the Rochester group then around that time. And of course, femtosecond lasers, you know, were really in the zeitgeist of the time. You know, even Doonesbury, you know, let's go on to some job openings, international currency issues. Anyone in femtosecond lasers? You know, parallel computer engineers? Nobody? Okay, so we clearly have left the Bronze Age. So this was in the air at the time. So there were some early successes at the first days at Rochester. The big program that was funding was the URI program. Was finishing off doing high-speed optoelectronics. Steve just talked about the development of the low-temperature gallium arsenide. This is the electro-optic sampling, you know, 1990 on the cover of Physics Today. And 1988 was a great year in another respect, of course, because this is when Ti-Sapphire came along. And so many of us remember Gary Valancourt. I guess Gary, he might have been able to make it. Just got to see him at CLEO a couple of weeks ago. So he had been at Quantronics, and he was basically working out of his garage in New York, and his little company working for Excel. And he had built his own neodymium YILF Q-switch and cavity, just Q-switch, and used that frequency doubled to pump Ti-Sapphire. So you had just a simple Q-switched Ti-Sapphire pump, and he had a little booth at CLEO in 1989. And so I was just wandering around the show and saw Gary, and I didn't know what he was up to, but I was excited about Ti-Sapphire because I'd seen Peter Moulton's talks on it and kind of dreamed up some ideas. I saw, oh, Gary already had a laser. I said, Gary, you got to bring that thing to Michigan. And so he literally, a couple weeks later, he threw it in the van and he drove to Michigan, and I furiously threw together a Styrol 9 dye laser. In fact, Wayne, I gave you kind of a phone call for some hints because I think you had also done the first sort of 750, 800 nanometer range dye lasers. And with Marcel Bouvier, we modified a Pockle cell so it would work. We had the same problem Donna had. The dye laser was in one lab. The regen was being built in another, so we strung an optical fiber over the ceiling. Now, this was no CPA because this was the year before the self-mode lock Ti-Sapphire. So Wilson said it was probably doing this at the same time. And so we got it to work a couple days before I had to leave for my postdoc in France. We got an optics letter that describes the first kilohertz pulse pump Ti-Sapphire, but it was picoseconds. There was no CPA there. And then when I left, then Jeff modified the spectrophysics Ti-Sapphire, got the self-mode locking, did the whole CPA business. And here it is. This is when they first got white light in I guess that would have been 91, I think, when Francois Salin and Jeff Squire really got that going. Now, sometime, for me, I was very excited about that and being part of it, but I had known from the first time I heard about Ti-Sapphire, the upper state lifetime is 3 microseconds, that meant that I could run at a much higher rep rate. And for me, wanting to do semiconductor physics and solid-state optoelectronics and so forth, a microjoule is enough. And so I wanted to run at a much, much higher repetition rate. And so we managed to cobble together some loaner parts, and of course I had to come up with a different way of switching, namely acousto-optic instead of electro-optic. And there's the final trace the day of the regen when we got white light. And you can see white light now being made in a piece of sapphire. And so that was really right around the time frame 1990 to 91. So 1990 then was the competition for the Science and Technology Centers from NSF. I believe this was the second class of STCs. It was the second competition. And we saw this as a great opportunity, and we knew what the foundation was. The foundation was this. We'd just done the regens, so I was very excited about being able to take that to do ultrafast. And of course, Gèrard now was extrapolating everything to petawatts. You hadn't got to exawatts yet in your discussions, but it was coming. And so we knew that this was the foundation. And so we had kind of a war room in what we call the Autumn Craft Room now, with Giannis and Steve and I sitting in there and trying to figure out how we made an STC concept, right? Because you have to do more than just share a laser. And we spent a lot of time in there. And we wrote, we wrote a great proposal, and the hype has the added benefit of being true, that we said it is precisely at this point in time, at this institution, that ultrafast optical science can most benefit from the establishment of a center to foster the continued growth of this exciting field of maturity. And that really turned out to be true. It wasn't hype. It really was true. Giannis, you came up with the logo, right? That was yours. That was yours, I'm pretty sure, yeah. And so we, the grand scheme, was simplicity itself, which is ultrafast optics is the foundation. Then there's both the ultrafast wing and the high field wing, and the science and technology both. I've sat on, I don't know how many NSF panels now for STCs and ERCs and MRSECs, and they show these org charts that look like something out of the Pentagon. Well, all this stuff, and things here and there, and it's just simplicity itself, and that's why it worked. The best ideas are the simple ones. So in '91, it was awarded. Everybody's very happy. Autumn's pouring drinks. Of course, we were very high tech. Here's the window to the lab. We had started off as the Ultrafast Science Lab. So somebody, put a little sign up in the corner now, Center for Ultrafast Optical Science. I don't know if the people who remember, this lab was next to the Great Lakes Research Lab. So they responded by, I don't have a picture of it, but you remember they responded by putting a sign up on their door saying the Ultra Slow Science Lab. And of course, STC concept was fairly new for NSF at the time. They reviewed us to death. I mean, we had an advisory board and an external panel review every year. They don't do that to centers anymore. It costs a lot of money, but it really holds your feet to the fire. And never forget Dan Grishkowski and others really just giving us a rough time so that they could go write a good report to NSF. I also learned that. So this is, I think this picture may be from the big review, which was the renewal in 1995. So of course we had about 30 faculty from many different departments. It's really a genuinely very interdisciplinary program throughout the 1990s with an evolving and generally growing population of faculty. I want to make sure we acknowledge, Serena Brown. I don't know, did Serena come today? Herb Winful was the director of the Education Outreach Program. I'll say a few words about that. And the center brought in Peter Pronko after Steve went off to start Picometrix, and Peter Pronko came in to serve as industrial liaison. He was a material scientist, so he played really a key role, not just in being the industrial liaison, but in bringing material science really into the realm of ultrafast. This is a partial and very incomplete list because we didn't really get all the advisors on here, but the center supported over 100 PhDs throughout the 1990s. And that's just a kind of list of the. One of the things that STCs and centers generally are supposed to do is have outreach programs, REU programs, start to involve undergraduates in a formal way, not just rely on the wisdom of a few people. This is just a picture from one of our early REU summer programs. This is a group. Some of you know Randy Bartels. This is one of our great success stories. Randy, of course, has gone on to become a fellow of OSA and American Physical Society and professor at Colorado State. So really starting people early is a great thing. Some of you may also remember that as part of the outreach effort, we had a booth for several years at CLEO. So Steve Kane and some of the other students were manning it, and this is people at the booth we had, and then Marcel and Medox there had a booth nearby. So tech transfer is, of course, in these science and technology centers. The technology is a key part of it, so you get your technology out there. One of the very first things that came out was, of course, the kilohertz Ti-Sapphire regens. We worked closely with Clark-MXR to make that happen. This is what the systems originally looked like in the early days. Eventually, they got them to be stable to the point where they could put this in the back of the van, drive it, park it, turn it on, and it works. And it works. So the 250 kilohertz, we worked with Coherent. So they basically branded that as the Reg A to go along with their Mira self-mode locked oscillator. So 250 kilohertz multi-microjoule system. The engineer there was Murray Reed, who transferred this. You can still buy this thing. It's still actually one of their solid sellers for scientific applications. Amazing 23 years later. At the time, I built that laser, I figured, lasers are on a 5-year life cycle. This will go for 5 years, and then Wayne will come up with something, and to leapfrog it. And the fiber laser people promised it, but for scientific applications, actually it hasn't happened. These things are still there. Another big tech transfer success story was Picometrix with the T-rays. I don't need to spend time on that. Steve's just given us a great story all about that, and the famous application of measuring the space shuttle tank foam. And of course, other big, just want to list a few of the main sort of things for which CUOS is known that happened in the 1990s. And of course, this is one of Gèrard's favorite and most famous juxtapositions, of course, is how chirp pulse amplification basically takes football field-sized lasers and lets you get those kinds of power densities by doing them on a tabletop. And there's Scott with the T-cube laser. I should mention the T-cube laser is alive and kicking, and in fact, Louise has just won an NSF grant to do a very significant amount of work on an upgrade and then use the T-cubed as a staging ground for doing things on the national facilities. So the T-cubed is there. And of course, the other thing is that pushing the pulse ever shorter and doing adaptive optics, then lets you get to relativistic optics and extreme intensities, now up to kilohertz repetition rates. So as a result of that, that gave rise to the famous, if not notorious, Mourou plot, which is the realization that, in the 1970s, there was a period known as stagflation in economics, and stagflation perhaps in lasers as well, until CPA came along, and now you can extrapolate to infinity, I guess. It's this particular version, it cuts off here, but we're still going up the same curve. So one of the other major advances, really, with the T-cube laser in the 1990s was the development of the very first experiments in relativistic optics and electron accelerators using terawatt lasers. 1994 to 1995, this is the publication was in January 95. So in 1994 was the discovery of self-channeling of high peak power pulses in air. That's the famous picture with Alan Brown and the hallway in IST. And I'm not going to say more about that. There's a talk coming up. You'll hear a lot more about that. Also in 1994, that was a good year. Right before the NSF renewal, with all these fantastic breakthroughs. Timing is everything in ultrafast optics, and this was an example. So Detal-Du in 1994 is the discovery of the deterministic breakdown of materials with femtosecond pulses extending the Bloombergen curve now to the picosecond pulse duration. Just for those of you who aren't familiar with how dramatic an effect this is a picture of some micromachining that was done with femtosecond pulses. So each of those is a single shot. And you can see that the size of the holes that you can make is tiny compared to the actual focal spot of the laser. It is so incredibly precise. And that has given rise to numerous applications in things like micromachining. Clark-MXR, for example, was one of the original licensees of the patent for this super high precision micromachining using femtosecond pulses. And of course, then you have medical applications that were envisaged. And this is, so this is the picture that really it shows the key difference between femtosecond pulses and nanosecond pulses. These are shots of images of what happens when you take an eye, you focus a femtosecond pulse beneath the surface, and you can get this very, very smooth cut, and long pulses just can't do it. And of course, that gave rise to the interlace story that you're going to hear more about in another hour or so with Ron Kurtz and Tibor Juhas, then bringing that whole concept to market. I should mention, just a couple of things. So CUOS is known for, pushing the frontiers of intensity, and most of the talks today are going to be on that. But there are other communities in which CUOS is really equally well known for fundamental science. So I don't have time, to go through the tremendous number of scientific breakthroughs. I just want to highlight, just a couple that came out to give some flavor. Tremendous amount of work in terahertz science, kind of complementing the terahertz technology development going on at Picometrix. Herb Winful and Van Rudd and John Whitaker and others doing the GUI phase shift. Some of our work doing things like time reversal terahertz imaging. There's a very young Roberto Merlin, who has one of the most highly cited papers in solid-state optics, really, in coherent phonons using femtosecond light pulses, because just about anybody who ever took a femtosecond laser and hit a sample with it saw the thing ring. So what he explained was why it rings, and it's a very universal phenomenon, and can study all kinds of things. A very young Duncan Steele here with two of the absolutely seminal papers in semiconductor quantum optics. First, really identifying the fundamental many-body mechanisms for nonlinear response in semiconductors, and then showing that by going to quantum dots, you could get to true artificial atoms. You had no longer a many-body optical response, but you had a true atomic-type response when you look at single quantum dots. And this work was funded by the CUOS Center, and it continues to be an enormously active field nowadays with the growth of quantum information technology and so forth. So the STCs had a finite 11-year lifetime. It didn't matter how well you were doing. Tough luck, that's the end. And so I remember we had a lot of talks at the end of the center as to what to do with it. And we decided, the best thing would be to turn it into a College of Engineering multidisciplinary center that would have multiple funding sources. The real successor to CUOS then was a physics frontier center that Phil Buxbaum put together called FOCUS, Frontiers in Optical Coherent and Ultrafast Science, which also had about an 8 or 9 year run. And then also post-sunset, CUOS continued to grow in several areas. Montes joined us, I believe, 2002 to bring high-power fiber lasers and push the frontier of high average power in ultrafast optics. And then after Gèrard returned to France, then we brought Karl Kruszelnik in to be the director, and then Alec Thomas. So we have really a world-class effort in high-field science, continuing building on that foundation. And of course, you've heard of the Hercules laser that Victor Antolia and others led, achieving the world record 10 to the 22. It's still held, right, by this laser system. And you'll be hearing more about that in other talks later today. So in terms of local impact, one measure is tech transfer and spin-off companies. Clark-MXR and Picometrix, I think, were the first. Then Transloom, interlays with the femtosecond eye surgery. IMR is not a spin-off here, but I think, it was attracted to Ann Arbor because of the tremendous activity in ultrafast brought here by CUOS. Almontes has founded Arbor Photonics in 2007, and we continue to start new companies based on work that's going on here in Michigan. Just a couple of months ago, we started Graphene Vision to to commercialize some graphene photodetectors and so forth. And so this is a picture from the dinner at Paleo's right before Gèrard and Marcel returned to Paris. So I think that picture came out very nicely. And I would say, you know, everybody, the buzzword these days in academia and so forth is, you know, impact factor. What's the impact factor on your journals, papers, things like that? I mean, the impact factor, as far as I'm concerned, of CUOS on many of us has been infinity. You can find yourself in here. This is a picture from the Distinguished University Lectureship that Gèrard gave, when was that, 2004? I think it was in 2004. So just a personal thanks from me to Gèrard. You know, he gave me a chance and encouraged me all along the way. It's been a fantastic ride. I would say that the thing I learned most was be completely fearless when you're doing science. And if you have an idea and you think it's a good one, just go do it. I mean, Gèrard, how much did you know about eye surgery before you started doing this? Negative, you know, perhaps. And so maybe I've made a fool of myself sometimes by launching into something that I didn't know anything about, but the risks are always worth taking. If you have a good idea, just go for it and just keep on exploring. So thank you very much. That's great.
So our next speaker is Silong Chen, and he's going to tell us about that cool picture